Okay, so, well, I guess it's time to get started slowly. So thanks everyone for joining. Today I will introduce how to use GIS in R, and this is going to be a pretty introductory webinar on the subject. But that's a topic that I really like, and I will offer more webinars on more advanced topic on GIS in R later on. So to get started, just so that you don't get surprised by what things will look like on my screen, just a little heads up, I ran R in Emacs using a package that is called ESS. Here is the package. So I am within Emacs here, and this is a script. I've called it webinar.r. So far it is empty because we'll work on it together. And here, this is my R session. So it's a way to use Emacs as an IDE. This is very much as if I were in RStudio. So my script's going to be on the left, and my shell, my R shell is going to be on the right. Then another thing that I wanted to show before we get started is this site that's called freegisdata.rtwilson.com. And by the way, I will post all of these references, all of the links on our website so that you'll be able to find them later on. But this is a site that's really great because it lists a lot of free GIS data, and that's a very good starting place if you're starting on a subject to see what might be available. Another thing that I wanted to show are the two data sets that I will be using in this webinar. The first one is the Randolph Glacier Inventory, or RJI. It's part of the GLIMS project. So it's open source, and they have been after one of the IPCC, like those intergovernmental panel on climate change, they have decided to map the all the glaciers of the world to keep a track of their evolution. But there isn't much data through time at this point. So what I will also use is a much geographically constrained data set, but it's close to home. It's in Glacier National Park. I will use this one because it has 4 nice little data sets in 1966, 98, 2005, and 2015. So that spans a pretty nice time range. And so we'll look at the evolution of glacier in that national park in those years. And lastly, another another resource that I will use in this webinar is called Natural Earth. And there are 2 R packages that allow to easily access this data. And that's one of the many ways to get very easily some base map information. So, but again, I will post those links on the site. That's just, I wanted to show you where things are coming from. So the very first thing we will do is to look at what the SF object is. R has had some GIS capability for quite a while, but the SF, which stands for a simple feature, it's a standard, and this set of standard was something that wasn't implemented in R until a few years ago, and that created all sorts of complications to transform data. So the reference R package when it comes to GIS analysis for the longest time was called SP, and SP is still being used, but a few years ago now, a new package called SF got launched to follow the SF or SFA for Simple Feature Access standard. Sorry. So this has now become the standard. In addition to that, for people who are familiar with the tidyverse in R, SF works in a fashion that is very similar to dplyr. And so all the data frame transformations that you are familiar to and that you are using all the time in two-dimensional data is something that you can apply in a very similar fashion with your geographic data. So the first thing that we will do is to load the library SF. So of course, for those who are fairly new to R, before you can load a package in R, you have to install it. But I'm not going to get into that at this point. I have already installed this package, so it is already in my computer. This is just a way to load it into this R session. And as you can see, the SF package uses GDAL, GIS, and Proj, which are big standard GIS libraries. Another pretty key package that we will be using is called tmap. And tmap is one of the main one of the main packages used to create maps, GIS maps in R. You can also use ggplot2, which is the most common plotting package these days. But tmap has some GIS-specific features that make it really convenient. By the way, I forgot to mention that SF is for vector data. For raster data, and that's a topic that I will cover on another webinar, but that we won't get into today. There are other packages, one of which is called raster. So, okay, let's load tmap. And then I told you that SF objects are can be played with in a fashion very similar to data frames. So we will actually load dplyr to play with the SF object in ways that are pretty classic. And then I will also load a number of other packages that are a bit more obscure, but MagritR is the tidyverse package for all the weird R pipes. The default pipe is loaded when you load dplyr, but there is a more obscure pipe called the assignment pipe that I will use, and to access it, you need to load MagritR. And then I will also load PER. PER is the functional programming library of the tidyverse. Then, remember I mentioned this natural Earth open data. The way to access it in R is through two packages. One is called R Natural Earth, and that's the package that has all the functions to extract the data, download some data, etc. And the other one is called R Natural Earth Data, and that's some data that is that gets pre-downloaded when you install it. But Natural Earth has a ton of data, and you can download more than what is in the R Natural Earth data through some functions. Okay, so let's start with that. So the very first thing that we will do is that we will load that the data from the RGI. So again, there is no interesting temporal information in that one. So that won't allow us to see changes in glacier area over time, but it will show us the distribution of glaciers. And I'm interested in our area, so I'll focus for all this webinar on northwestern North America. So I first downloaded the data from the website, and this is what the data looks like. It's a very classic shape file. This, by the way, is it's called Ranger, and it's just a file browser that runs in the command line. And so I downloaded this directory from the RGI website, and in this directory you can see, for those who are used to GIS in maybe ArcGIS or QGIS, the very classic shapefile files that you would load in a GUI. So we will load them into R in a way very similar to what you would do in an ArcGIS GUI interface. Oops, yeah. So in order to load this data into R, we will use one of the SF function that's called stRead. And all of the SF functions start with st underscore. That makes it really easy to identify them and also to autocomplete. For instance, if you're in RStudio or in some other IDE that has auto completion functionality, you can just type st underscore and then have the various SF functions show up. And ST stands for special type. So stRead is the one to read in data. So I am running R in the same directory in which I have downloaded this data. So after stRead, you need a full path or an absolute path or a path relative to your R session, because my R session is in the same place as the directory. I can directly copy the name of the directory. Sorry, wrong window, paste it here. And I will create an object. Let's call it West for Western North America. So there we go. So I have just created an SF object that contains this RGI data, so the data of those glaciers in North America. So let's explore this SF object a little bit. You can, of course, print it, and the output looks a little complex. So when you print it, what R tells you is it's a simple feature. So simple feature collection, that's an SF object with 18,855 features. So those correspond to the rows, and 22 fields. Those are the column. The geometry type, that's the SF, the simple feature standards that are implemented in all sorts of contexts. Because SF is totally compliant with those standards, multi-polygon is the classic type for data that is made of several polygons. Dimension XY, that means that it's a two-dimensional data. You can have up to 4 dimensions. A third dimension is if you have something that includes elevation. And the fourth dimension can be some other attribute, can be temporal, can be some other attribute. But here we only have 2 dimensions, X and Y. The B box, that is the boundary, the box of the boundary of our SF object. So the B box always has minimum X, minimum Y, and then maximum X, maximum Y. Then you have the CRS, so that's the coordinate reference system, because of course the Earth is not a sphere, but sphere-ish, and we are plotting here on a two-dimensional space. So to go from a three-dimensional reality to a two-dimensional representation, you need some transformation. And there are very many transformations that are more or less suitable depending on the context. They all have some advantages and disadvantages. Some are very easy to understand, some distort areas, some are very good at a small scale, some are better at a large scale, etc., etc. And so the CRS, the coordinate reference system, is very important to keep in mind, because if you import various data sets to combine them or to compare them or to build several layers, if they don't have the same CRS, of course, you're gonna have some really surprising results. And then those are the first 10 features. So I told you that the features are the rows, so they're the data points. So this is the head of our data frame. So those are the first 10 rows. And so it is almost a data frame. I mean, it is a data frame, except that the last field is, and it's always at the end, is called geometry. And geometry is actually a list. So you have a data frame that follows all of the data frame characteristics, but the last column is a list column. That's the only little complication of the SF object compared to a classic R data frame. And so just a little bit of nomenclature. So SF is the type of the SF object. So that's the entire data frame with its little weird list column. SFC for SF column is the type of that particular very unique geometry column at the end. And SFJ, G, sorry, J and G in French are reversed. So SFG is the type of a single feature. Other than that, it's all your classic data frame. Let's run structure on it. Let's pass it through the structure function so that you can have a bit more info on that. So the classes are SF and data frame. So it's a data frame with its list column, but it's also an SF object. So it belongs to two classes. We had 18,855 features and 22 fields. Well, we have 18,855 observations. So again, the observations, those are the rows, and 23 variables. So we have one additional variable compared to the number of fields because of the SFC structure of that last column. So the first variable is called RGI ID, RGI against the data set. So it's the ID. The type is character. So it's just the name of each observation. And by the way, each observation, each row is one individual glacier. So we are looking at 18,855 different glaciers, one per row. And then there is an ID in the glimpse system. There are some begin and end dates. Those are when the data was collected. But again, it's not that the full data was collected at various times. It started to be collected at a certain point and then ended later. So it doesn't give us a chronology of the glacier evolution. So it's not something we're particularly interested in. Then you have area, slope, aspect, etc., etc. So we won't use all of this data, but we can keep it all in this, we're just going to keep things simple for this first example. Let's look at the CRS. We already saw it when we called WES. We had geographic CRS, VGS 84, which is one of the very classic CRS. But you can also run, so again, ST, that's the prefix for all of the SF functions, STCRS WES. That gives us the same information, VGS 84, but there is some additional information, including the EPSG. And the EPSG, so that's the geodetic parameter dataset. And the reason it's called EPSG is some historical reason, because EPSG stands for European Petroleum Survey Group, and that's the group who started to implement this before it became a standard. And so even though it has nothing to do with petroleum, it's still called EPSG. So each CRS has an EPSG number that identifies it, and it's better to use this number rather than the more human understandable name of the CRS when you want to transform things. And there are some functions, and you can also find it online to translate from the classic human name we are familiar with and the EPSG. But so these glaciers, this first data set is in VGS 84, which corresponds to the EPSG 4326. Okay, so we could plot it with the default R plot function. That works. So that's going to take a little bit of time, because this is not how you want to plot GIS data. I'm just showing to you that it works, because we have all these variables. And if you just plot the object, R will plot a different map for every single variable. So that's going to take forever, because it's a fairly large data set, and you're going to have a bunch of little maps, one for each object. So I'm going to let R do its thing in the background, but this is not great. Much better options to plot are either with ggplot2 or what we will do today with tmap. So when you plot with tmap, the first thing that you need is so ST is the prefix for SF, TM is the prefix for tmap. So, and again, the underscore is very aligned to the tidyverse syntax. And so those packages, Tmax and SF, they are fairly modern packages. And so they're very aligned to all of the tidyverse packages from Hadley Wickham and the RStudio team. So they will feel very familiar very quickly if you are used to those modern R conventions. So TM shape is the way to define a layer. If you are familiar with GIS in a GUI interface, you have various layers and you can select them, unselect them, move them around, and you display layer on top of layers. This is exactly the same, except that each layer is a TM shape. So the TM shape here is this layer of data, WES, but TM shape alone doesn't do anything. You also need to set some aesthetics for the for how you want to display the layer, and that's very similar to the grammar of graphics followed by ggplot. So if you want to get some information on the various no, it's still plotting here. If you want to get some information on the various options, you can run, I think it's tmap element. I think this is the, but let me double check. Well, maybe I'll stop this because this is taking forever. Yeah, I think I will I will stop this. But as you can see, we already have one map that is displayed here, and I'm sure this is totally invisible to you, but at the top, there is a little title that says RGIID. So that's the RGIID, that's our very first variable in our SF object. So there are another 22 to be plotted. So let me kill this if I can. Well, let's see. Am I going to kill the R process? Well, if I kill the R process, it's no big deal. Let's try that. It's taking a little longer than I thought it might. Okay. Yeah, okay, that killed the R process. That's okay. I'll restart it. Okay, so I am reloading all of the packages. I am rereading the data set, but this time I'm not gonna run plot because this is not great. Instead, I am gonna run tmap. So I believe that to get information on all the element, it's tmap element, but let's try it. Yes, it is. Okay, so tmap element gives you the various ways you can display your shape, so your layer. So you have TM fill that creates a polygon layer without the borders. TM borders, that's the polygon borders, but without the fill. And then you have TM polygons, which creates the polygon and the border. Then you have all sorts of other things with raster and lines and etc., but they aren't relevant for us because we are dealing with polygons exclusively right now. Like our glaciers are polygons. So we could use TM fill or we could use TM borders, but if we use TM polygons, that will print the polygon itself and its border. Polygons, is it? Yes. Okay, so it's printing, so it's thinking. There we go. Okay. So instead of having 23 of these, one for each variable, tmap only prints one with whatever you will ask it to print. So this is not great, but it's a starting place. To orientate yourself a little bit, Alaska would be at the top left. Of course, there are many glaciers in Alaska. The reason they're not part of the RGI dataset is because they haven't been fully mapped yet. It's an ongoing project. Then you can see like the southern part of Alaska is there, and then this is like Yukon and BC and Oregon, and then it goes all the way down to California. So, okay, so those are our glaciers, but that's not exactly a great map. So we can add a bit of information onto it. So for instance, we could add a compass. So there is a tm compass function. And again, always, if you want some information to remind yourself, oh, what are the arguments that I can pass to tmas compass, you can always use question mark and then the function, and that will open some help file in which you will have the list of arguments with their default value. So that means that if you don't pass a new value, this is the value given to the argument, and some explanation for each of the argument and some example. The help files in R are great, so do make use of them. So here we will use the type arrow. There are some pretty crazy types, actually. Some really very navigation fancy type, but arrow is the most like the most simple. Then you can set where you want your compass on the map. So you can set some exact coordinate, but you can also do something pretty easy, such as right or center or left, then top or bottom, etc. So we'll go with something easy. Actually, I'll show you what happens if I stop there. So it's plotting. As you can see, like I don't have a prompt yet, so that means that R is thinking. Up, I get my prompt, so that's done. Okay, so here is my little compass. It's a little small, so I'm gonna add another. I'm gonna replace one of the default value for the argument text size, and I'll put it at 1.5. Okay. Actually, yeah. So now I have a compass, but I can add more layers. I can, for instance, put a scale bar. A map without a scale is not really useful. So again, you can look at the help to see all of the values. You can set the breaks that you want for your scale. So the break argument accepts a vector. So I will use 0, 100, and 200 kilometers. Kilometers are the default, but of course you can also change that. And again, so as not to have minuscule text size, I'm gonna change the text size. Okay, so let's, oh, I have a wrong parenthesis somewhere. Oh yes, no, actually, I'm not sure. I'm not sure where my wrong parenthesis is. Okay, so I have tm shape plus tm polygons plus tm compass plus tm scale bar. I'm not sure. I'm looking at my notes and I don't see what I did wrong. Okay, well, let's do. Okay, so this worked. So it's only the TM scale bar. I see. It's because it's not called break, it's called breaks. Okay. All right, I found it. Little typo here. Okay, so now this is going to work. So I am replotting my map with all my glaciers, but this time I have a compass that's a little bit more visible, and more importantly, I have some scale here. Okay. That's still not amazing, but it's getting better. We can also add things like a title. And so title, legend, and all of the customization of the title, the legend, etc., are added with the tmax function called tm layout. And this one, to get information on it, it's question mark tm layout, and it has lots of customization about the title, the legend, the different colors and sizes, and etc., the style. So I will add a title, for instance, glaciers of northwestern America. I will set the title position. It's very similar in for the syntax as the TM compass. And we could have also changed the position of the scale bar with the same syntax. It's just that by default, it's at the bottom right, which I think is pretty good. So the title will make it in the center top. By default, it's at the center left. Well, and again, fixing the size. Okay, so now I'm gonna have a title for this map. But that's still not absolutely phenomenal because we don't have any base map layer. We only have the actual data in the form of almost 19,000 polygons, each polygon representing a glacier. But it's hard to see that this is the west coast of North America. So it would be nice to add some base map to that. And there are many options. There is one library that is pretty cool that's called ggmap that allows to download and plot the base map using OpenStreet, for instance, or all sorts of other open source GIS. But a very cool option is actually to use tmap itself. Tmap comes with two modes. There is the mode called plotting, and that's what we've been using so far. And there is the mode called view. And you can switch from one mode to the other by running tmap mode view or tmap mode plotting, but you can also run the function TTM, which stands for type of tmap, I think. And each time you will run, no, it's toggle tmap mode. Yeah, TTM stands for toggle tmap mode. Each time you will run TTM, you will toggle from view or plotting. So there are two options. So if I run either of these, now tmap is set to interactive viewing, and I could rerun my previous map, but there is also a function that allows you to do that very easily, and it's called tmap last, So tmap last simply rerun the last plot we've been running. So I have a little warning here that in view mode, compass is not supported. Okay. And I don't have a prompt yet, so R is working. But when it is done, I will have the same map open in the browser with all those with some of those open source layers, such as OpenStreet plotted. Okay, so I have also another warning that the scale bar breaks are ignored. Okay, no worries. So now I'm moving to my browser, and this is what opened automatically. So this is using Leaflet GIS. So tmap just creates a wrapper around some of the Leaflet functionality, but that's just very simple. Here you can access, so you have OpenStreetMap, you have World Topo Map, and you have the World Gray canvas. And then you have your layers. So because I have run only one TM shape in this map, I have only a single layer. But in the same way that you can stack multiple layers in a GIS GUI, you can stack multiple of these. So you can add plus TM shape and then add some new data with its TM fill or TM polygon, etc. And you can stack however many you want. And you would see those here, and you can toggle them. Like you can toggle your layer as you would in a GUI. So you can select OpenStreetMap, and that's what you could have on your own static map if you downloaded the data with the ggmap package. And you can have the S3 World Topo Map. And of course, it's interactive, so you can move around, you can zoom. And so it's a bit slow because it's a very large data set. It's got 18,000 polygons with all those glacier, but it's pretty cool. So let's zoom in a little bit more. So you don't even need ArcGIS or QGIS if you want to just visualize your data in some really easy way. And I didn't have to download the S3 Topo Map or the OpenStreetMap because thanks to Leaflet, it's all there. And yeah, so I think that's pretty cool. Okay. Oh yeah, so you have the scale here, right? Anyway, our map, though, if we want a static map without using Leaflet, isn't all that great because we don't have a background. So instead of going for some of those very heavy data sets like OpenStreetMap, we can also use the natural earth package. And so the R natural earth has the functions that allow to retrieve the data. And so they all start with NE underscore. So again, they are following the same tidyverse style with a consistent prefix and underscore. And so the natural earth states allows you to print the states of countries or all the things that you choose. There is an NE countries if you only want the countries. There are very many options. Some have physical features, so you can have streams and etc. Some have urban features, so you can have buildings and all sorts of urban attributes. So there's a lot of data, but you can pick and choose what you want to download in a way, instead of having like OpenStreetMap that downloads everything in a big layer, you can pick and choose the attributes you want, and it's pretty cool. So that's a neat package. And because our map has various provinces, there's BC, Alberta, etc. Instead of using any countries, I will use any states. It's more appropriate to what I want to print. So again, you can question mark any states to find the default for that function, but that function accepts a number of arguments, and one of them is country. And this natural Earth has data for the entire globe. So we don't want the data for Australia. We're interested in Western North America here. So for the countries, I will select Canada and United States of America. So one criticism I have for this package, it's maintained by the R OpenSci group, which is phenomenal, but I find it poorly documented. For instance, I couldn't find any documentation anywhere that told me what the list of countries were. So in order to find that for the US, I had to type United States of America. It involved some trial and error. So maybe I missed something, but I really looked for all relevant information and it wasn't easy at all. So I tried USA, I tried various things. So documentation is a bit lacking, but the actual data is phenomenal. Okay, so one thing that is important is the return class. There are two possible return class, SP and SF. And because SP was the standard for so long, the default, unfortunately, is SP. So it's important to add return class equals SF so that we don't create an SP object, but we create an SF object. So let's call it states. I am here creating a new SF object thanks to this natural Earth package, and it will contain the natural Earth data for Canada and the US. And you can, as I said, this package comes full of functions, and so you can have various level of precision. So you can have some very light files that are suitable for very zoomed out maps, and then much more high res and heavier files for very zoom in maps. So, okay, so I have created this new SF object called states. Let's plot it. We can use the same code we've been using earlier, but now instead of using it on the West object, we're going to use it on the states object. So it's working. Okay. Oh. Where is my map? Oh, did I run this? Yeah, I did. Okay, let me close this. So R is thinking. Oh. Okay. Why is it not? Oh, yeah. Okay. Yes, I know. Yeah, because the natural Earth package is so full of data, I have to actually select the column that I want to plot. Unlike with our Glacier data, I didn't have to select which column I wanted to plot. I could just run tnshape I could run my all SF object through TM shape. Here, I won't be able to do that. That's why it's not plotting. So let's explore states. So it is a simple feature collection with 64 features and 83 fields. The geometry type is also multi-polygon. It's also two-dimensional. The CRS is the same, VGS 84. But as you can see, some of the features are, some of the fields, I mean, are very complex. They involve a link to Wikipedia and all sorts of things. And that's why you can't just plot it like that. You have to select what you want to plot. And the variable that makes most sense for us here is name in English. So name in, those are all the state names. So again, for the US and Canada in English. So states is an SF object, but it's also a sort of data frame. So you can use the syntax you're familiar with. If you run, something is not working as I expect, because everything was working this morning. So I must be doing another little typo or something. Okay. Let's see. Any states? The country, I chose Canada, United States of America. Return class SF. Okay. So why? This is surprising, because that was working. Oh, okay. I know. The reason nothing was showing the entire time is entirely my fault. Remember that TTM allows to toggle tmap mode. Well, I ran tmap mode view. So I entered the tmap mode interactive view that opens in the browser. And then I didn't revert to the plotting mode. So the entire time I was wondering why nothing was plotting, and I was puzzled. In fact, things were working just fine and plotting just fine, but they were things were being plotted in the browser. Okay, that's why. So there we go. So if I ran TTM, now tmap mode is set to plotting. Again, I could have run tmap mode plotting. So now, if I run the same very basic tmap code to create a single layer with the states SF object I just created and showing the polygon, this is what I have. So the reason the map is so stretched out is because we have the end of the I forgot their name, but some of the islands at the bottom of this thing in Alaska, I forgot the name. But anyway, unfortunately, they're over there instead of being over here. So, which is why the map is looks so stretched out. But it worked. But again, we are only interested in what is in this area. So I need to filter only the states that I'm interested in. So if I run okay, this is still not working. Because it's name without a S. Okay, so I was making several mistakes. So if I run states and then the $ name English, which is the classic R way to index a column in a data frame, you can see that it works just fine. So our SF object behaves like a data frame, and I have the list of all the states. So I will filter it using what I would do in dplyr. So with a pipe and with filter, that's dplyr filter. So name English, equal, I'll choose Alaska. And then if you want to use filter, dplyr filter, and have multiple conditions, you have to use the and or syntax. And okay, so then I will also select for British Columbia and for Yukon. And because we don't have a lot of time, I'm not gonna enter all of the provinces I'm interested in, but you get the idea. And I can create a new SF object, let's call it BG for background, for instance, this way. And so background is an SF object that only has the rows that correspond to Alaska, BC, and Yukon. Because in this states SF object, each row, each data point corresponds to one polygon that corresponds to one state. So I can then plot this. So instead of states, now I put background. And I have only the states that I have selected. So if I remove Alaska, since the end of Alaska here is stretching, I would have a better map. But some of Alaska has glaciers that are being mapped in the south. So there is a much better way to crop to the area we're interested in using bbox. If I want to look at the boundary dimension of an SF object, the function is stbbox. So the stbbox of my background are here, but the the bbox dimension of Wes are a lot smaller, and that's because of this those Alaska islands. So what I can do is that I can run tmshape background with bbox equal stbbox Wes. And this shows my background map, but cropped at the boundary, the exact boundary of Wes. So if you want to map multiple layers on top of each other, the main thing that is very important to pay attention to, of course, is the CRS. You don't want to have some mismatch of CRS. But another thing that you want to pay attention to is to have matching bbox, because otherwise you may have some maps plotting just a small area into larger maps, and it's just chaotic. And now I can combine both of them. Remember that they have the same CRS. So there's nothing wrong with combining them as they are. We don't have to run a transformation. So we will stack the WES layer on top of the bbox layer. The other way around, remember, it's as in a GUI system, the top layer would cover the bottom layer, so that wouldn't be as good. So I'm gonna copy this. And then plus, and then I can add that map here with a title and all the little customization that we did earlier. So R is thinking. So scale bar set for latitude, kilometer, and will be different at the top and bottom of the map. Okay. Okay. I used the wrong layer. I used state instead of background. So let me do it again. Remember that background was with only Alaska, BC, and Yukon. Okay. So, oh, and I forgot the B box, geez, which is why I have this mismatch. I warned you about it, and then I'm doing it. There we go. Okay. So now I am correcting this. Okay, so I am plotting background with the bbox of WES and polygon, and then I'm adding a new layer, so TM shape WES, and all the things that we plotted before. Finally, phew. Okay, so this is what I'm getting. So that's starting to be a little bit better. I didn't do it out of lack of time, but of course, if I had added Washington, Oregon, and California, you could see that I would have those bottom provinces there. So this is just because I'm trying to finish soon. Then you can also customize this. You can make the glacier of a certain color and play with the transparency, and you can create more fancy maps. But very quickly, before we leave, I will show you, and I will open the file to save time because I'm so slow. I will show you what I think is more fun. So by the way, yeah, this is my whole script. Those are my notes. So let's actually run the whole thing with a full background. So, okay. So here I'm doing the same thing that I was doing with you, but I added all of the proper provinces, states, and then I made a few colors. So just to show you a few variations. So now my glaciers are in blue, and I've only plotted the borders of the states layer. But what is much more interesting is to see the evolution of glaciers over time. And for this, I will be using that other data set, which only focuses on one national park, but which has 4 very neat and similar data sets, starting in 66, which is fairly early. So I won't get into a lot of detail, but there were lots of inconsistencies in the names, in the order. Some the variables were sometimes in capital letter, sometimes lower letter. They were flipped around. So I did a little bit of cleaning. So what I'm doing here is that I'm creating an object called deers. I can print it. That is a vector of all of the directories in my current directory that starts with GPN glaciers. I'm using regular expressions here thanks to grep. And that's a way to load and transform those 4 data sets in one go in a vectorized fashion rather than have to copy paste the code 4 times, which is always a bad practice. So then I created a function that I'm calling prep for preparation. And that function is what will prepare the data. So first I need to read it with stread. Then I need to rename it. Each data set has a column called area with the year. So there's area 1966, area, etc. I'm renaming them into simply area so that I can bind my 4 data sets and like stack them into a single data set instead of having 4 different data sets. And then I am passing my names through 2 lower so that they're all in lowercase. And I'm using select to reorder so that all the variables are in the same order in all data sets so that I can bind them properly. And this weird thing here, that's the assignment pipe. That's the reason I loaded the Magritte R package at the start. And what it does is that it pipes and then reassign. So it's the equivalent of having the object, assignment, the same object, and the regular pipe. It's just a shorter form. So I'm creating this function. And then I am using map from the per package, which allows to do functional programming. So I am running dirs, which is my vector with the 4 directory names with my 4 data set through my prep function all at once, thanks to map. And I am creating an object that I'm calling G for Glacier, and map outputs a list. So G is actually a list of 4 elements, and each element of that list is an SF object. So it's not a very nice format. It's a bit of a clunky object right now. I'm trying to go to the beginning. Right. So if I were to print G, so see, this is the 4th object of the list, and it's an SF object. And then you have here the I went through the 3rd object of the list, that's an SF object, etc., etc. So I have a list of 4 SF objects. If I run this object through rbind, thanks to do call, I compact my list into a single data frame. So I'll have a single SF object with all my data stacked. Since I've cleaned it all nicely, I can do that. So, okay. So now G is what we are familiar with. It's an SF collection. Each of my 4 data sets had 39 features because that national park has 39 glaciers. And so because they're all stacked now, I have 4 times 39. I have my 39 glaciers for the year 1966, and then my 39 for the year 98, etc., etc. Because I have a year column, it's all good. And at the end, I have my geometry list column. So it's good actually before you stack a bunch of data sets together, as I did, to double check everything. So I actually, well, now it's too late because I've run the code, but I did double check that the CRS were the same for all of the element of my list before I compacted my list into an individual SF object, because it would be terrible to have different SF objects with different CRS combined into one. So it's important to do some checks, and I checked for the equality of the CRS between all objects, and it all came true, so that was all good. Okay. Now, if you look at the CRS of G, those 4 data sets had the same CRS, but they all have a CRS which is NAD83, which is also a very common CRS. So if I wanted to use this map in combination to the WES layer that we created earlier, which was in VGS 84, I would have to transform it. So the way to transform a CRS from one format to another is thanks to the SF function stTransform. So if I run stTransform G, that's my new SF object with my 4 different years of the 39 glaciers and stCRS of WES. Now, if I run stCRS of G, it's been transformed to VGS 84. So now this new SF object is in the same CRS as my WES object, and I could combine them to have those 39 glaciers, for instance, as an inset of the larger map. So I could print, I won't have time to do it, but I could print a big map with all of the glaciers, and then for the small inset, that temporal aspect. And if I print that object, that SF object G, this is what it looks like. So those are the 39 polygons for the 39 glaciers. And let's focus on just one, and then I'll leave at after this, and to see the retreat of glaciers on one glacier. So I will filter out of the G object the glacier called Agassiz Glacier. So there is one variable called GLACName. So I'm filtering with dplyr filter, GLACName equals Agassiz Glacier, and I'm creating a new SF object called Agassiz, which is just a subset. And then I am plotting it. So this is the Agassiz Glacier, and it has several sets of borders because there are multiple data points corresponding to the 4 different years. So that's not very easy to see what's going on here. But you can run inside polygons, you can use a palette, for instance, a palette with the blues on the year variable, and that will color code the polygons per year following a palette. So obviously there are very many palettes, but one with a uniform color, since this is not different variables, but the same variable that's evolving over time is quite suitable. You can, of course, fix the legend sizes so that they're not so minuscule. And by using a minus sign with the palette, you can flip the color around. So I increased the font of the legend and I reversed the color. So in 1966, this was the outline of the Agassiz Glacier, and then in 98, and then in 2005, and then in 2015. And of course, it would be good to add a little scale. And you can even create an animation. You can, and that under the hood uses GG Animate, run TM shape, Agassiz, TM polygons, so the same thing we've plotted before, but add a TM facets, and then use the tmap animation to create a GIF that shows how the glacier shrinks in an animation. So first you need to create the anim object, and then I just created an anim.gif, and it's over here. And I'm not gonna keep going because I've already kept you past the hour. I'm sorry for being slow. But if you build a website or if you were in a Jupyter notebook, or if if you were building some little widget, you could have the glacier, the GIF animated showing the evolution of the glacier. So today was very preliminary. It was very introductory. It was just a very short introduction to the SF object and the tmap package that allows to map very easily. But there are bridges between QGIS and R with the R QGIS package. There is the raster package that allows to deal with raster data instead of vector data. You can use ggplot instead of tmap to plot. And of course, you can do some actual analysis, because today we've just been plotting, but you could do much more, like all of your GIS work in R. So I intend to give other webinars on this topic again, because it's a topic that I really enjoy. And I thank you for your patience. I apologize for keeping you so long. And if you have any question, I will try to answer you. So please unmute yourself and ask away.